Okay, very good. How many people know what stacking is? Never heard of it. Okay, all right. Who knows how it works, basically?
At the end of the meeting, you'll get the chair.
Yeah, I'm the same way too. Yeah. Okay, so I'm the same way too. So this is going to be very short. All right. But anyway, so yeah, that's the title of it: exposure stacking in a nutshell. Basically, we're going to show you exactly how, well, not exactly, but roughly how taking multiple exposures and, quote, combining them into a single long exposure can give you yield good results while dodging noise and whatnot. Okay, so what I have up here right now is a short exposure. This was taken in Apex, probably like 2015, I think is when I took this, and so I wanted to try out just taking, going after something that was really faint in a place where the light pollution was not super bad, but not that great either. I wanted to try to go after something faint and just try out and see what would happen if I went for 100 exposures. And so at I started at 120, and I was looking at it, and I was like, okay, well, I can kind of see something there. Let me push it to 130. Well, that's when I started getting that little yellow tone that you see there in the single exposure on the left. So I was like, okay, well, we'll stop it right there. And stopping it right there, I went ahead and just recorded all night, 130 seconds exposures, or 280 minutes roughly, if you want to call it that. So, but anyway, so good times. Very long night, but then again, even when your skies are dark and your exposures are great, it ends up being a long night anyway. So anyway, so how do we go from a single exposure that's only 130 seconds to something that's 140 times 130 seconds is? I don't know how many seconds that is, so somebody can do the math in your head, go for it. But anyway, so I mean, what's the point of stacking? Okay, so the biggest thing that most people think about is signal to noise, and we're going to elaborate on these 3 points, and that's pretty much going to be the whole talk. But one of the things that I ran across on the internet, because I was just trying to find something that was a nice summation of how stacking works. And there's the link down there. What I'll do is I'll email the link. I'll somehow get this presentation out to the Yahoo group, and that way you'll have this and you can just look it over if you want. But that article that was in Sky and Telescope, that was a good way of explaining how stacking works. And so anyway, so we'll talk about to increase why stacking, what the whole point of stacking is, and it's to increase signal to noise. But you want to, the signal is the actual object you're taking a picture of, right? And the noise is everything else that you don't want. So, so the other thing too is every camera is different, so you want to exploit how well your camera works, and that's the second point, to reveal the dynamic range of the camera. And obviously, you want to make the bottleneck, which is the post-processing, after you have grabbed all your exposures and you're about to stack. Afterwards, you get your stack. Well, it's not going to look 100% like that on the right, so you're going to have to tweak it a little bit. Okay, so probably what would have been a better talk this time around would probably been registration and calibration of your individual frames, like the single 130-second exposure frame on the right, but because stacking is pretty much the second step, but we're going to do it anyway. So anyway, so what's the point? Again, first point that we got to was increasing the signal to noise ratio. I'm not going to go into the math that much. This article that I was pointing to down here, the link goes into it. Gives you a good good explanation of what it's all about, and also I got one image that kind of helps us understand exactly what's going on when we're trying to increase the signal to noise ratio. And like I said before, the signal is what's coming from the object that you're trying to take a picture of. Let's just say that you're boring and you're just taking a picture of Sirius, the star. Okay, the star, Sirius, bright star, night sky. But anyway, well, those photons are coming in when they're hitting your sensor. that's all that's going to hit there, okay, as far as signal, because that's what you're taking a picture of. You're collecting light from that object. And okay, so that's why I have always constant in there. Now noise is everything else that you don't want to be in the picture. You want the blackness of space and the signal coming from the object you're taking a picture of. So basically, coming back here, I don't want that yellow. I don't want any grainy noise. You can't really see it here that well. But what I do want is I want to get rid of that yellow so that I can see that object on the right a lot easier. And well, you can probably pretty much see like there's a lot more stars on that stacked image on the right. So anyway, so types of noises that you run into, well, camera noise. So there's read noise coming from your camera. There's somebody say other noises coming from the camera. Dark current and what else?
You're going to have just random noise on the pixels.
Yeah, random noises. If you get hot pixels that'll pop up once in a while. Okay, other forms of noise, again, it's everything else. Well, you get light reflections. Hopefully you don't have a right light reflection on all of your exposures, because we'll show you a little stacking algorithm where you can remove things that may come across an exposure here and there. You have airplanes. All of us have encountered trails of airplanes going across our exposures, and they just they're pretty much light pollution onto themselves around here because we're so close to our new airport. So, and then light pollution. That's probably the hardest thing to overcome, obviously. So, why I put there, if you have too much on time on your hands, this can be reduced. As in, like, if you're willing to drive out where light pollution is not much of a problem, then yeah, noises from light pollution is not going to be a problem. So, oh, thank you. Okay, exposure, again, what's the point? So, increasing the signal to noise ratio. The thing I like about this graph right here is it goes back to what I'm saying about how noise falls onto the pixels of the sensor and how signal falls onto the sensor. Now, as you're taking exposures, which are down there on X, you're gathering signal the whole time. Those pixels are picking up the starlight from every star. Say like you have Sirius, going back to that example, the pixels that are in the area where the star Sirius is that you're going to be using your camera to expose, they're always going to pick up light from Sirius. That light that it's always going to be picking up is signal. So with every exposure, you're gaining more and more signal from that object. In this case, we're talking about Sirius. Now, noise is everything else that can get in the way, as we said earlier. So you may have camera noise getting in the way, whether it be like hot pixels or fixed pattern noise. There was another one I could have thought of. That's going to get in the way of the photons coming from Sirius going into that pixel and collecting it. So you're going to have noise being collected there. You're going to have signal being collected there. However, as long as you keep your camera under control, like keeping it cool and whatnot, your noise can only get but so bad per exposure, okay? But your signal is always going to be there. It's always going to be there. It's going to add up with time. So eventually, the more exposures you make, the higher your signal to noise ratio is going to be. So basically, so noise will always be present throughout your exposure, but not necessarily on the same pixel. Okay, there are exceptions like hot pixels that will always have noise, and then you have light pollution. If it's a nice even lit field or lit sky above you, you're going to have light pollution. So that's pretty much always going to be in the same spot. But signal will always follow the same pixel, and given time, overwhelm noise falling onto that pixel. That's why the line for signal there is higher than noise. And so, anyways, the second point, we want to reveal the dynamic range of the camera. We're trying to, again, going back, we're trying to exploit how well our camera works. Okay, so you'll find one statistic about the cameras that are out there of how much dynamic range of tones of whether it be black and white like we have here, or different wavelengths of light or whatnot. Okay, so some sensors are able to pick up hydrogen alpha. That's on the red side of the spectrum that is given off by a lot of nebulae. Some don't. However, in the collective sense, dynamic range is exactly how much tunnel width you can pick up on the cameras that you're using. Now, if you have a camera, God forbid, if it even exists, that has 1 bit dynamic range, okay, you're only going to have 2 tones. You're going to have black and you're going to have white, and that's it. Okay. So every time you go up dynamic range, you increase the power of the number of tones by. Your base unit is 2, okay? Because your lowest bit value can only be black and white. Now, as your dynamic range or number of bits in your dynamic range goes up, you're basically raising the power to 2, okay? So here we have the base number 2, and a 2-bit dynamic range gets us 4 new tones. We have black already, we have white already, but now we have one tone that's not so black, and then we have a dark gray, then we have a gray, and then we have one that's almost white but not white. And so keep going on, and you see how the math starts to add up. Okay, I guess most affordable cameras that are out there go up to like 12. Am I right, guys? When I say affordable, I mean as in $3,000 or less.
My MC,
Anybody want to interject or?
my MC 178 is 14-bit.
14-bit?
It's 14-bit.
Okay, all right. Okay, well anyway, yeah, I'm used to, well, the cameras I've always researched usually go up to 12, and anything above that is just beyond my pocketbook, so, or wallet, rather. Okay. Okay, so we're dealing with dynamic range of the camera. In one exposure, noise may hide the signal's true value of a pixel and in turn reduce the potential of that camera's dynamic range. Okay, so again, we have a noise mixing in with the signal that we want. So the signal is going to always be there, but who knows, maybe in next exposure that pixel will be clean. It'll only have signal in it. So by stacking more exposures, you increase the chances of the pixel recording the signal's true value, as in the actual photon coming from the star series. Okay, is what you're trying to record. So in the case of light pollution, faint signal like that of a galaxy's arms or faint nebulosities is best remedied by just going to a darker site or investing in technology to combat light pollution. And the shortcut you may hear about this around the club is narrowband filters, which block a lot of light. However, it lets through the wavelengths that we're most interested in. And narrowband filters are purely mostly for just taking a picture of nebulae. So that's what they're used for, because the emission nebulae, they're giving off their own types of photons, and usually they don't overlap too much with light pollution. I mean, if they do overlap, then you may need to buy narrower narrowband filters. And the narrower your bandwidth of your narrowband filters, the more expensive it is. So feel free to interrupt me if you have a question or whatever. And if I don't know the answer, I know somebody else here does. So revealing the dynamic range of camera. Well, so if I do a few exposures, yeah, I'm starting to pick up some nice nebulosity there. This is H alpha, by the way. This is through a narrowband filter. This is a section of Pelican Nebulae. Preparation for this, I went out and took some pictures or images of Pelican Nebulae, so I could just like somehow have something to demonstrate what's going on here when you have a few exposures versus lots of exposures. So the camera I was using is black and white, so I'm sorry if it's not interesting, but when I collect 2 more data sets of narrowbands, I can assign each one to the additive RGB color scheme, where I can say that, like in this case, H alpha or hydrogen alpha, that's what you're seeing here, can be this band's green, blue can be oxygen 3, and then red can be sulfur 2. Sulfur 2 and oxygen 3 are 2 other types of wavelengths that come out of nebulae that we use narrowband filters to image. So anyway, obviously you can see there, more exposures, the cleaner the image starts to look. Okay, so this is basically the reason why I posted this is just so that you can see finer detail in just a given area of the whole image. This is just a crop of a section of the Pelican nebulae right here. So, or nebula, rather. So, you have 5 on the left and 20 on the right. So, the more exposure you get, the cleaner your signal comes out to be, because the noise does change, you know, as from exposure to exposure, and but the signal does not. We'll just continue to accumulate it in each of the exposures, and when it's time to stack, we'll be able to combine them all.
So Chris.
Yes, sir.
Question. Back to that other slide. If obviously 10-minute exposures require a pretty good amount, what if somebody doesn't have a really expensive mount, or they have a little bit too much weight on it? They can get away with doing maybe a 2-minute exposure.
Like 2-minute exposures, yeah.
But instead would they get similar results if they could do like 40?
Like 40 or so. Well, yeah, I mean, because it goes back to, you know, this guy right here, right? So, but if you notice the square root of what is it, inverse square root? Anyway, so you see that the noise is going down, but it will never like go completely down, okay? But your signal will continue to climb. So if you want to do shorter exposures, eventually you'll get to the point where you'll have something like that on the right, okay, with shorter exposures. But you're only gaining like, let me just put it this way, okay, so trying to answer Mike's question, like, oh, well, can we do short exposures if our mount's not that good, or if we don't have narrowband filters and we're forced to do short exposures, okay? So let's just ignore these numbers right here, signal, noise. Well, let's say that picture I just showed you, these are 10-minute increments, okay? So I'm gaining a lot of noise as I go along, but if I do 2-minute increments, I'm going to be gathering just a little bit as I go along. So what will happen is, that's roughly speaking, I mean, it's not really a good way of explaining it, but you can eventually get the same signal to noise as you would, it's such a mess right now, as you would if you were taking a 10-minute exposure, but it's going to take quite a while to get there, okay? So, but depending on the kind of camera you have, so again, some of the noise that comes from the camera, if you have a good camera that has low noise, you can picture that that line of noise being flatter with the camera that, say, like has lower read noise. So then your signal will tend to pop through faster, I mean, obviously. So, but yeah, you're right. You can take a lot shorter exposures, and eventually you'll get to something like that, but it may take quite a while.
And some may want to start out with a DSLR because they don't want to invest in a really expensive actively cooled camera.
Yeah.
And you can get great results. You can't push the sensor too long, you know, because it heats up.
Did everybody hear that? Yeah, can you come forward?
Okay.
Can you come forward and explain that again?
I'm just saying, when I started imaging, I started with a Canon T2i for 2 years. To this day, it's still some of my personal best work. But the problem is, it wasn't actively cooled. Some of the best work that I got from the camera was during the winter when temperatures got down to about 20 degrees and we were out doing imaging, because then it was cool. But a camera like that doesn't like to be, because it's not actively cooled, the sensor, like any electronic device, will heat up. And the noise level, the intrinsic noise levels will increase. We use actively cooled cameras now, and you don't have to worry too much about that. But if you want to start out with just a DSLR, which I advocate for all new imagers, just to see if they get the bug, you know, and that's why I was mentioning shorter exposures.
Well, he's pretty much gone the path that I took. I mean, that's what I had when I first started out, was a DSLR. So it's nice all-in-one thing that you just put into your
Sorry.
no, that's fine. Into your telescope. But anyway, it's all in one package. I guess that's what I'm trying to say. But anyway, but yeah, what he's getting at as far as like temperature goes, temperature or thermal noise. As your thermal noise goes up, it starts to overwhelm the signal again. But again, the signal eventually it's just going to get to a point where it'll peak. And once it peaks, again, the signal is still going to overwhelm it, okay? Anyways, let's see, where are we? Okay, so that's 5 10-minute exposures. We do 20 10-minute exposures. We get a cleaner signal. You may be asking what that black line is at the bottom of the right image. That's actually, this is from 2 nights of imaging, so my alignment wasn't perfect there. So it's like, yeah, it was off a little bit. I don't like to go into details, but anyway. Okay, so next, if we were to, if you remember those first 2 images that I showed you at the very front of the presentation right there, you'll notice how one of them, the one on the right, looks nice and pretty and mostly clean. I mean, it's the best I could do with considering the equipment I had. But the other one, what if I were to process, post-processing, which is what the next part after you've done your stacking, what if I were to process that single image rather than processing my stacked image? Okay, well, if I apply all the processing techniques that I do to a single image that I would with a stacked image, you'll get something like that. Okay, yeah, sure, you can see the nebula better, but it looks pretty damn ugly. Okay, so, and that's basically because we're not only are we trying to enhance the nebula, but remember, the noise is still there in the way, okay? So you only have but so much signal there, and it can't pierce through all that noise right there. So again, stacking more, well, makes it easier to get through noise, and post-processing will give you a clear looking image. Yes, sir?
Do you take every picture exactly the same, like ISO and seconds that you stack? Is it always the same exact exposure settings?
No, not necessarily. You, Rob. Okay, I was trying to figure out. I couldn't tell who was saying that. Okay. No, not necessarily, because like everybody knows how, or most people who have gotten into astrophotography, we all like to take a picture of the Orion Nebula. There are going to be places in your pictures that are like really, really bright. Like right here, for example, this is the star Alnitak. Everybody likes taking a picture of the Horsehead Nebula. However, because that bright star that's so close by, sometimes if you're like taking a picture at a longer focal length, like when I say longer focal length, or you don't really catch what I'm saying, if you're like zoomed into this section right here, well, you're going to have this really bright starlight coming out from the side, and that's Alnitak right there. This starlight from the star Alnitak right there. So how do you tone that down? Well, like he's asking, can you do like different exposures throughout with your data set that you're going to stack? Yes, you can. What you can do is you can do like say like 30-second exposures and stack those, okay, independently. And then you can do like I did here, 2-minute exposure, 130 seconds, close enough. Anyway, exposures and stack those, okay. But what you can do then is you can do what's called high dynamic range compositing, and you can do that in post-processing, where what will happen is in your longer exposures where you're seeing all that annoying starlight coming from Alnitak there, you can use like Photoshop or whatever to tone that down while keeping all this nice nebulosity around there from disappearing or whatever. But anyway. Okay, so stacking algorithm. So I'm just going to go through Deep Sky Stacker, and I have Deep Sky Stacker here on my laptop here. And one of the things that Deep Sky Stacker, before it gets to a stack, if you remember earlier in the talk, we were talking about other things that you have to do to your exposures before you stack them, or very advisable things that you should do with your exposures before you stack them. Okay, so that's called registering and calibrating your exposures. Okay, so I'm not going to really talk about that. I mean, yeah, I'm not really going to talk about that. But the 3 most common algorithms that you'll find in Deep Sky Stacker that I use, actually entropy weighted average. I've only used that a few times, but average, which is most common, and then sigma kappa clipping, which is used. You'll see why that's useful. So first, an average stack. So we're going to do the Pelican Nebula, hydrogen alpha. So I'm going to Deep Sky Stacker. All right. right, so I've already calibrated the images. What I was talking about, registering and calibrating the images. I did dark frame subtraction, and that's all I did actually. Sensor is so small on this thing, I hardly notice any uneven field illumination. So, okay, here we are. So, let's see. Did I have them registered? Yes, they're registered. Okay, good. Okay, so open picture files. Okay, so what I'm going to do is I'm going to show you the Pelican Nebula in hydrogen alpha wavelength. So this is just one wavelength of light, and I'm going to stack these images, and these are the images that I showed in the PowerPoint here, back here. Okay, so that's a small section of the picture that you're about to see right there. Okay, so let's see. Okay, so here's my darks. Let's see, there's more darks right there. Okay, that's, I'm gonna throw that off. Sort by type. That's better. Okay, I'm looking for my lights. Okay, these are the individual. Oh, that's so dark. These are my individual exposures that I used to take a picture of the nebulae on hydrogen alpha wavelength. So what I was using is I was using a monochrome camera, and I had a narrowband filter in front of it, so I could filter out everything except for the hydrogen alpha wavelength. Refresh my memory, what's the wavelength for that? Is it 565 or 656? 656. 656, okay. I go dyslexic on that number all the time, I don't know why, but anyway, so 656 nanometers is where hydrogen alpha photons fall on the electromagnetic spectrum. So choose all these right here, and I'm going to open them. They've already been calibrated, so we're not going to see any of that silliness. Okay, so let's look at a single exposure and see what it looks like. Okay, I need to stretch it here. So you can kind of see the nebulae coming through right there a little bit. Really black one. So you can see it looks kind of flat. I mean, the tones are not too bad. For a sub, this is really good. And the reason why I say this is really good, that's because this one has been calibrated, okay? It's been calibrated. You saw that I had some there that are labeled darks. If you want to see what a totally uncalibrated frame looks like,
Are you calibrated? You apply the darks?
I've already applied the darks to it. Okay, so I didn't do any biases on this night. I was looking for 2 biases with this camera. So this is what, well, that's North America. I don't want that. I don't want Pelican. Look at this guy right here. So that's what it looks like right there. So it's not super clean looking, okay? If we zoom in, take a look at it. Okay, so it's kind of noisy, it's grainy, it's not really nice and fine, but anyway, that's what a single exposure looks like right there. So that's the Pelican Nebula. Everybody can see the Pelican, I assume, right? Good. Just say yes, Chris. I can see it.
Yeah. Yes.
Actually, here,
yes, Chris,
yeah,
I can see it.
I get distracted so easily. This right, I like the Pelican Nebula right here. This is part of the North American Nebula right here. That exposure that I showed you earlier is like out to here. I really wish I would have gone up further this way. I'm going to do a 2-panel mosaic. Eventually, maybe I can get it done this weekend. Who knows? But I think the favorite thing that I ran across, my favorite thing that I ran across while I was taking this picture, did anybody see the Deadpool nebula?
Yeah.
Yeah, isn't that cool?
That's very cool.
Yeah, he's laying on his head. I mean, laying on his side there. But yeah, there's Deadpool's head right there. So anyway, I thought that was cool. Anyway.
I hadn't heard that one. That's cool.
So anyways, I don't know why it does this, but when I open this, and I've heard other people complain about this, but my images come up mirrored in Deep Sky Stacker for whatever reason. So the Pelican Nebula is actually flipped, or the way it appears in the sky is actually flipped. So it's backwards there, but for our purposes, I don't really care. But let's see. So let's go ahead and stack this. So what we wanted to look at first was averaging, so that's what we're going to do first. 20 minutes. Okay, so let's see. Go ahead, so. Oh, this is set at cap signal. We'll get to that later. Let's do averaging. I won't get into auto adaptive weighted averaging and stuff. We'll just call it averaging. Anyway. So